In this lecture, we're going to cover terrestrial planets. When we talk about the terrestrial planets, the one we know the most about is the Earth. And so we're going to start out by looking at all the details of the Earth, and then we're going to compare the other planets to Earth. Okay, so let's start out with the density. The density of the Earth is about 5,500 kilograms per meter cubed. Now, I want to give you some numbers to help you get some idea of what this means. 1,000 kilograms per meter cubed is water. So that's a baseline, 1,000. The next is 2,000 to 4,000 kilograms per meter cubed. 2,000 to 4,000 is rock. So anytime we talk about rock, we're going to be doing 2,000 to 4,000. The water on the surface of the planet is only 1,000. Notice the density of Earth is about 5,500 kilograms per meter cubed, which is greater than the 4,000, which is the high end for rock. This means that the center of the planet, or at least some part of the planet, has to be more dense than rock. Okay, so basically that's how we figured out that it has to be more dense at the center, is by looking at the density of rock and then comparing it to the overall density of the Earth. We can also determine that there's something at the center of the Earth by looking at how the S waves and the P waves move through the Earth after an earthquake. I'm going to leave that though for your geology teachers to cover. Okay, so let's talk about the parts of the Earth. We're going to start out with the core at the center. Then we have the mantle, the crust, the hydrosphere, the zone, which is actually another way of saying the atmosphere, and then we'll talk about the magnetosphere. Okay, so inside the core we have very high pressure and very high temperatures. We have an inner core, which is solid, and then we have a liquid outer core. The mantle is dense rock. It's not molten, but it's not solid either. It acts more like a plastic. Then we have the crust. The crust is thin. It contains the continents and also the ocean floor. The hydrosphere is the water that covers the surface of the planet. 70% of the Earth is covered by water. 2% of that is in lakes. 68% is in oceans. The oceans range at most about 3.6 kilometers deep. Okay, so let's talk about the atmosphere. There's lots of advantages to having an atmosphere. One is that it provides us with oxygen. That's not actually from the atmosphere itself. It's actually from the plant life that produces the oxygen through photosynthesis. The atmosphere also protects us from radiation, and that protects us in several ways. Certain layers will protect us from UV radiation. Some layers actually store that radiation for us in order to warm up the atmosphere. The mesosphere and higher is actually the place where we have meteors burn up. So here, when it says protect against meteorites, basically it burns them up enough so that they become small chunks. And that's much less dangerous than being hit with this big, huge block of rock. Okay, there's also surface heating which occurs, and that energy gets trapped. That keeps us warm. If we didn't have the atmosphere on the Earth, our daytime would be very, very hot and our nighttime would be very, very cold. Okay, so in order to have temperatures temperate where we can live, it's the atmosphere that traps that radiation. The ozone layer actually protects us from UV radiation. Part of that UV radiation does get through, and it's actually trapped close to the surface by the greenhouse gases. We call this a partial greenhouse effect. And we actually need to have this partial greenhouse effect. What is dangerous, though, is when the Earth's whole global system cannot maintain equilibrium. In other words, if we produce more carbon dioxide and other greenhouse gases than can be stored or eliminated from the Earth processes, mostly trees, then we run into a problem. We end up with more greenhouse gases than we need, and that starts to heat up the planet as a whole. Okay, so let's talk about the percentages for the atmosphere. 78% of it is nitrogen, about 21% is oxygen, 2 to 4% is the water vapor. And then look at the percentage for CO2. Only 0.038% is carbon dioxide. The thing is, though, is that carbon dioxide is very, very, very good at absorbing and keeping ultraviolet radiation close to the surface. It sort of acts like a barrier and it won't let it back through. And you don't need a whole lot of CO2 to make that happen. Okay, so let's talk about the layers of the atmosphere. Closest to the Earth is the troposphere. There's a boundary between the troposphere and the stratosphere, which is caused in the change in temperature. So the way that we determine these layers of the atmosphere is by looking at the temperature. In the troposphere, the temperature decreases. Then all of a sudden, the temperature remains constant, and then it starts to increase in temperature. At that point where we see it going from decreasing to increasing in temperature, we call that the tropopause. The reason that the next layer is heating up, which we'll call the stratosphere, is because of the ozone layer. The O3 molecules in the ozone layer actually keep the UV radiation from coming down into the troposphere. So that causes the air in the stratosphere to heat up. Okay, so as soon as we get to the point where it starts, the ozone layer stops and the layer starts to cool again. Okay, so from the stratosphere, it goes up, the temperature increases, increases, and then it stops increasing and starts decreasing again. At that point, we call it the stratopause. Okay, so the stratopause, let me actually put this right here. Here would be your tropopause right here. Sorry, I can't draw straight with this with my finger. This is the clouds. Clouds are in the troposphere. We have the ozone layer, and then right here, the temperature starts to decrease again, and that's the mesosphere. Then, as we hit this boundary here, the temperature starts to increase again, and let me go ahead and draw this. So the temperature would decrease until we hit the stratosphere, then it starts to increase, and then it starts to decrease again, and then it starts to increase through the thermosphere. So that's kind of how the temperature works. Now the thermosphere is actually made up of two sublayers, and actually the ionosphere starts in the mesosphere. So we have the ionosphere, which is in the mesosphere and the thermosphere, and then the exosphere is the highest part, and that's basically space. The magnetosphere sits above that. Some of it, though, does enter into the atmosphere, and you can see that at the poles. So when we look right here and we look right here, these magnetic field lines are actually within the Earth's atmosphere. And when the charged particles that are trapped by the magnetosphere hit those gases, we're going to form our auroras. Okay. Now, how did this magnetic field form? We believe that it's due to the liquid outer core, which is believed to have ionized particles. Also, there are probably metals that have been ionized. As they move and rotate inside the Earth, they're going to produce these little tiny magnetic fields. Those magnetic fields are going to add up to form the two large spheres, which you see here and here. You can see one here, and then there's another one. Those are called the Van Allen belts. So there's two big spheres of magnetic field that sit around the Earth, and those are your Van Allen belts. Okay, so the magnetosphere has two poles, a north pole and a south pole. I'm going to really confuse you now. The South Pole is not the pole that's on the south of the Earth. Okay, so right here's a pole, right here's a pole, and then you can see the two belts that make up the Van Allen belts. They're right here and right here. Those are the two loops that make up the Van Allen belts. Now, this is actually the south pole of the magnet, and this is actually the north pole of the magnet. The magnetic field lines come out of the north and go into the south. Our compass is actually measuring where the electric field or where the magnetic field lines are going into. So the magnetic field lines actually loop around this way and go into the top of the Earth, which is the south pole of a magnet. Okay, but our compasses are made to actually line up with those magnetic field lines coming out of the south and going into the south pole, the south geometric pole, and going into the north geometric pole. But it's actually the opposite as far as the poles of a magnet are concerned. Okay, so like I said before, the magnetosphere comes in contact with the atmosphere at the poles, the magnetic North Pole and the magnetic South Pole, and that's going to form your auroras. Those charged particles that are being trapped by the magnetic field lines are actually going to bombard the materials in the atoms, and molecules in our atmosphere, and it's going to cause them to give off radiation. And that's what the different colors are. They're actually the gases in our atmosphere that are glowing because they're being hit by these charged particles and they're getting excited. So in the North Pole, we have the aurora borealis, which you can see in Alaska. And then we have in the Southern Hemisphere, the aurora australis, which you can see in Antarctica and the lower parts of Australia. Okay, so let's talk about plate tectonics. We have a lot of evidence to support plate tectonics. So some of the things that happen due to plate movement would be earthquakes, volcanoes, and mountain ranges. Okay, so when two plates come together, one of those plates will slide under another, and that's what we call a subduction zone. Okay, and when two plates are moving away from each other, that's going to form your mid-ocean ridge. So you can have a subduction zone, which is going to form your volcanoes, and then you can have a mid-ocean ridge. There's also where two plates, continental plates, come together. That's where you're going to form your mountain ranges, and that's what's happening with India. India is moving into the Eurasian plate, and that's actually forming the Himalayan mountains. Okay, so now that we've had a brief review of the Earth, and like I said, I'm pretty sure that those of you that have had your geology courses or are geology majors, you're going to know a lot more about the geology of the Earth than I do. And so please send me little notes if there's something you caught that was wrong so that I can fix it. But I just wanted to give you a general idea of what was going on. So now what we're going to do is we're going to talk about two objects in the solar system which are very closely related in looks and appearance and size, but they're not the same in the sense that Mercury is a planet and the moon actually goes around the Earth. So we're going to talk about these two at the same time because they have very similar features. Okay, so let's talk about the moon. The density of the moon is 3,300 kilograms per meter cubed. That sits between 2,000 and 4,000, which is rock, and that tells us that there's no heavy metal core to the moon. We believe that the moon could have been formed with a collision of an asteroid with the Earth. Probably more recently, they've looked at planetesimals. During the formation of the solar system, there were a lot of planetesimals forming and colliding with one another, breaking apart and reforming. And I think that the current most accepted theory is that there was a very large planetesimal that collided with the Earth, not head on, but off at an angle, that planetesimal skid off of the surface of the forming Earth, carrying with it the outer layer, so to speak, of the Earth material. It broke apart into lots and lots of pieces, and then eventually coalesced into what we have today as our moon. The moon is only a quarter of the size of the Earth, but it's rather large compared to the other moons in the inner solar system. In fact, no other planet has a moon that's actually spherical in shape. Mars has 2 moons, but they appear to be captured asteroids from the asteroid belt. And so it's kind of unique that Earth has such a large moon. The moon is only 1/80th of the mass of the Earth, so it does not have as much mass. Also, the moon has no significant atmosphere. It cannot trap radiation from the sun, so the bright side is hot and the dark side is way below freezing. Probably, I would say probably close to, space, which is about 10 to 20 Kelvin. So it's very, very cold on the dark side. For the side that's being bombarded with the sun, it's going to be much warmer. But that radiation cannot be trapped and held in place because there's no significant atmosphere. Now, recently they did launch LADEE, and LADEE did take measurements, and I believe there's been other probes that have been sent to the moon by other countries. And they have found evidence of a slight atmosphere, but it's not significant. Okay, so let's talk about the surface features on the moon. There are these 14 lava beds, which are flat and also very dark in color, and they call them maria. And if you're looking at a single one, it would be mare. Okay, there are no maria on the dark side of the moon. So if you were to go to the other side of the moon that's not facing us, you would not see these dark features, these lava beds. It is possible, and in fact they've actually verified this, that ice is trapped in these craters. If they're deep enough, the water can actually get in there and freeze, and because the sun never comes in contact with the bottom of the crater, it actually freezes in place and stays there. So there is evidence of ice just under the surface, and that means that there is most likely ice, water ice inside these craters. Okay, there are craters, many, many craters, and in fact, some of them are quite beautiful. You can actually see the rays that come out of the crater from the material that was inside the moon that has spread out or exploded outward. 1 moon day is equal to 1 moon year. That means that the moon rotates and revolves at 27.3 days. So that means we're going to always see the same side of the moon. So if this is difficult for you to understand, I'm going to put up a clip and hopefully this will help you. This is really a difficult concept also for teaching students. Even high school students and college students have difficulty understanding what the rotation rate is and what the revolution rate is and how they can be the same. In other words, how is it that we only see one side of the moon? Okay, so I'm going to go ahead and put a video clip up to help you with that. Okay, so let's talk about Mercury. Mercury has a density of about 5,400 kilograms per meter cubed. Notice that that's greater than the 4,000, which is rock. That means that it probably has a dense core, and we believe it's iron. The size of Mercury is quite small. It's only 38% the size of the Earth, and it's only 0.055 times the mass of the Earth. So you can see it's almost just slightly larger than the moon. There is no atmosphere, significant atmosphere to Mercury. It does have traces of hydrogen and helium, which are trapped by the planet from the solar winds. Also, there are traces of sodium and potassium that are being ripped from the rocks by those solar winds. But those materials are not held in place for a significant amount of time and so it's not a significant atmosphere. Okay, there are a few lava flows on the surface of Mercury. There's mainly highlands, and this is also what we see on the other side of the moon. When we look at the other side of the moon, the dark side, the side that's, let me put it this way. The other side of the moon is not dark. We call it the dark side of the moon because it's the side we don't see. So it's kind of a misconception or a misworded way of saying the side of the moon that's dark, because it's not dark. During a new moon, it's actually bright on the other side of the moon. But on the other side of the moon that we don't see, there are highlands, there are no lava beds. So the surface of Mercury is very similar to the side of the moon that we don't see. Okay, so let's go ahead and look at Venus and Mars. Venus has a density of about 5,300 kilograms per meter cubed. That's about 96% the density of the Earth, so it's slightly less. The Earth is, remember, around 5,500. It's about 95% the size of the Earth and 82% its mass. Its rotation axis, now this is unique, is tilted 117.4 degrees. So Venus actually rotates clockwise instead of counterclockwise. We believe that probably there was some collision that occurred during its formation, which caused it to completely flip to give us that 117-degree angle of rotation, or that what we call a retrograde orbit. It's clockwise instead of counterclockwise. You can see Venus in the early morning before the sun rises or right after sunset. It can reach as high as 47 degrees above the horizon. So if you see a very, very bright object in the sky just after sunset where the sun has set, or just before sunrise where the sun is coming up above the horizon, that very, very bright object is most likely Venus. The atmosphere of Venus is opaque. We can't see through it. We've actually had to send different probes to actually radio map the surface. It's 96.5% CO2 and only 3.5% nitrogen. The surface temperature, because of all the CO2 and because of its close proximity to the sun compared to us, is a constant 750 Kelvin. Okay, so the temperature of Venus is extremely hot. In fact, hot enough to melt lead. Also, because of the high concentration of CO2, it has a very, very high pressure. The outer atmosphere is sulfuric acid. This is a runaway greenhouse effect. So in other words, there are no cold spots on Venus. That means there's no ice. Also, something interesting, Venus does not have a magnetic field. So we believe probably it does not have any type of a liquid or flexible core inside the planet. Also, there's evidence of things in the upper atmosphere, like ice and stuff like that, so that there's actually a possibility there could be life that can form in that upper atmosphere. Okay, so let's talk about some of the surface features. There are craters on the surface, there are volcanoes, and there are what we call coronae. We've also seen evidence of mountains and valleys, which are actually quite beautiful. If you look at an animation that's made from the Magellan data, it's quite beautiful and breathtaking. This coronae actually appear to be upswellings of the mantle material. They usually have volcanoes on and in them. And actually they have these flat features that look like pancakes. And we call them the pancake domes. It's sort of like, I don't know if any of you have gone to Luray Caverns, but it's sort of like those little, the eggs, the sunny side up eggs that have been formed from the water that drips down to start forming the stalagmite. So it's a flat surface and it looks like a pancake. The coronae, though, go around that and they're actually quite wide compared to those pancake features. Okay, Venus has a 117-day rotation. It takes 226 and a half days to revolve. That's a 1-to-2 ratio between the rotation and revolution rates. And what we find is that all of the inner planets have these whole number ratios, which allows them to stay in orbit. Okay, so let's talk about Mars. Mars's density is very low. It's only 3,900 kilograms per meter cubed. That's only 71% of the density of Earth. And that also falls between the 2,000 and 4,000, which is rock. It's only 53% the size of the Earth, and it's only 11% of its mass. This is actually a very small planet. Even though its day is 24.6 hours, which is close to our day, it's still very small. It does take 687 days, though, to go around the sun. The atmosphere is again predominantly carbon dioxide and a little bit of nitrogen, 0.13% oxygen, and 0.03% water vapor. It is 50 Kelvin cooler than the Earth. So 50 Kelvin, let me put it this way. If we were at 20 degrees Celsius, which is 70 degrees Fahrenheit, then it would be below freezing at all times. Because 50 Kelvin difference is the same as 50 degrees Celsius difference, or Celsius degrees difference. So 50 degrees below 20 would be negative 30 degrees Celsius. So way, way, way below freezing. It is a very cold, frigid planet. It's not a nice place. There's these wind storms that come up, and you have these dust storms that cover the entire planet, so that sunlight does not get through. And it's got a lot of large rocks. It has mountains. It has valleys. It has huge craters. And so weather-wise, it's really not nice. I'm not sure why people want to go there. I would rather go to the moon than go to Mars. At least on the moon, you don't have to worry about a sandstorm or a dust storm knocking down your habitat. There are other things you could do, though. You could, there's actually these tubes, these lava tubes that have been formed. I guess you could go through those lava tubes and actually build a habitat underground. If you did that, then you could probably maintain the temperature, and you would also remove the hazards of the dust. So that's something to think about as far as colonization is concerned. Okay, Mars does have 2 moons. They do appear to be captured asteroids. They're not spherical in shape. They are Phobos and Deimos, which mean fear and panic. And since Mars is the god of war, they're pretty appropriate names for their moons. Okay, there are polar ice caps on the surface of Mars. It appears to be, from the sampling we've taken, frozen CO2. There are craters, rocky areas. There are channels, so it does appear that water flowed in its path. And actually, just recently, they've actually had recorded evidence of flowing liquids on the surface. So here you can see some pictures. You can see splash craters, which suggests that there was water present in the crust. There also appear to be these channels which would form from running water or moving water.